Did you ever ask yourself what is a network protocol, or how do devices communicate? Let me explain it to you. So to understand how two machines communicate, we first have to look at how humans communicate and then see what machines need to do differently. So let's say we have two people and they speak to one another. We use our voice, hand signaling, body language, or facial gestures to convey our idea to the other person. The other person uses their eyes and ears to register the messages and then uses his or her brain to process all of that and come to a conclusion. So the person on the other side can even be saying one thing, but based on our earlier history, they can mean something entirely different. For example, the person can wink so nobody sees, and you will know that they are not telling the truth, or actually mean something else. Another situation would be if we were to stand behind someone speaking for a big audience. The person in front of us can be saying something, but cross their fingers behind their back to signal us that they don't really mean what they're saying. So again, we would use our eyes and ears to register the messages and then use our brain to process all of that and come to a conclusion. Having that in mind, we can say that communication between people is a communication between two intelligent creatures. But do computers, smartphones, or machines have intelligence, and how do they communicate? It turns out they don't. This is why they need a whole different way of communicating in order to convey their message from one device to another. Let's see how this happens in real world. Here we have two smartphones communicating, and the smartphone on the left needs to send a message of hello to the smartphone on the right. How do they achieve this without eyes, mouth, or ears? All they can use is wireless waves. First, they need to determine a value for each letter in the alphabet and each sign they want to use. So we can say, for example, A equals 1 wave, B equals 2 waves, C equals 3 waves, etc. And we need to determine value in waves for each letter or sign we want to use. But the next question is, how would the receiving device know when a letter starts and when a letter finishes? Or what wave is the start of the next letter? Not to mention that the more letters and signs you want to use, the more waves you need in order to convey them. If, for example, you want to use multiple alphabets or even emojis, you would need dozens or even hundreds of waves for only a single character. This is resource and time consuming. That being said, we have two main issues to solve. First, when does a letter start and finish? And second, how to reduce the number of waves for each letter. Luckily, we have come up with a better way of doing things. If we introduce a dimension of time to this communication path, we can drastically improve our communication. We still have two smartphones communicating, and the smartphone on the left needs to send a message of hello to the smartphone on the right. But this time, we will say that every letter or sign or emoji must be conveyed within 1 second, or a frequency of 1 hertz. The hertz is the unit of frequency in the International System of Units, often described as being equivalent to 1 event or cycle per second. Who said so? Wikipedia. Now imagine again we want to convey the message hello to the other smartphone. How would that look like? Following our initial logic, for each letter of the alphabet, H would take 8 waves, E would take 5 waves, L would take 12 waves, L again would take 12 waves, and O would take 16 waves. Well, you can see this will be a problem. We know that with every second a new letter will be communicated, but the thing is, we don't have enough time to convey certain letters in 1 second, even the ones with the least waves. So how do we solve the second issue? We introduce something what is called data encoding. Let's say we must encode every sign using 8 bits, and we have only 1 second to convey each letter. The receiving device will listen for incoming waves and register a wave or no wave every eighth of a second. But what is even better, we can use the alternating voltage to represent some voltage as 1 and some voltage as 0. And we will call each 1 and each 0 a bit. The bit represents a logical state with one of two possible values. These values are most commonly represented as either 1 or 0, but other representations such as true or false, yes or no, on and off, plus or minus are also widely used. Again, who said so? Wikipedia. In other words, a bit is the smallest chunk of data that a device can transmit or receive, and every single thing is communicated using bits, no matter how complex. Movies, songs, pictures, conversations, surveillance cam videos, Facebook messages, etc. Let's move on with our example. Using bits, we can create a much better encoding scheme that would look something like this. We can say A will be a 1 followed by 7 zeros. B would be 0, 1 followed by 6 zeros. C would be 0, 0, 1 followed by 5 zeros, etc. And we will define a value in binary with 8 bits for each letter or character we want to use. You see here, with right data encoding, we can convey so many more characters within 1 unit of time. It was 1 hertz for our example, or 1 cycle per second. In the modern world, we have multiple encoding standards used by different operating systems and applications, but they primarily use UTF-8. You can see in this article how each character is represented. A link to the article will be in video description. Now, how does this tie to network protocols, which was our original question? Well, each network protocol serves a purpose and needs to communicate some specific information from one device to another, or from one application to another. Bluetooth, you know what it does. OSPF only exchanges IP reachability information between routers. HTTP only used to transfer hypertext, aka web traffic. And in order for this information to be successfully communicated, we need both or all devices taking part in this conversation to understand and speak this specific protocol. So here it is even simpler. These strings of zeros and ones are identical in binary. But if they were communicated in different protocols, they would carry entirely different meanings for involved devices. We can use our analogy to character encoding mentioned earlier. You could have the same binary values for multiple different letters. How so? Because we are communicating an entirely different alphabet, and the receiving device is also expecting an entirely different alphabet. In reality, today's machines use much more efficient and effective data modulation techniques, where they're able to transmit multiple bits with every clock cycle. This kind of progress enables us to transmit high amounts of data with low latency and high reliability. This technology is what enables you to watch this video right now. So hopefully you now have a better idea on how machines communicate in comparison to us humans, and how network protocols work. Thanks for watching, and stay tuned for more.